In this video, I'm going to prove the following theorem. It has a number of parts. It says that let n be greater than 0. That means n is positive, and it's an integer. Let the positive integer n be fixed, and a, b, c, and d be arbitrary integers. Then the following 6 facts are true. That a positive integer is congruent to itself for any mod n. And if a is congruent to b for any mod n, then b is congruent to a for that same mod n. If a is congruent to b, and b in turn is congruent to c, all mod n, then you have the transitive property. A is congruent to C mod n. If A is congruent to B and C is congruent to D, then you can add A and C, you can add B and D, and those two sums will be congruent to one another. And their products will be congruent to one another. Now, why do I say congruent to one another and not A is congruent to B mod n? Well, that's one way of reading this. But remember, this is true, and we're about to prove it, if and only if B is congruent to A mod n. I think this was, yep, it's right there, number 2 above. Okay, so basically A and B are congruent to one another mod n. Because if A is congruent to B mod n, then B is congruent to A mod n. We can just say A and B are congruent mod n. I should write out congruent, but I'm being lazy. Okay, so you don't have to say A is congruent to B mod n. Just say A and B are congruent mod n, if you feel like it. Sometimes it's better not to say that. Number 5 says that if A is congruent to B mod n, you can add C to both sides and they're still congruent. In fact, you can multiply A by C, there it is, and multiply B by C, there it is, and they'll be congruent. And here's a nice one. If A is congruent to B mod n, then A to any positive integer power is congruent to B to that integer power. And that's going to be quite useful to find out if two numbers are congruent to one another, or to check for divisibility. Okay. So let's get right into the proof. The proof of the first one. A minus A is 0 times n. Well, remember, if A minus B is some number times n, that implies, by definition, that A is congruent to B mod n. I don't care if A and B are the capital A and capital B are the same. I don't care that C is 0. Just keep in mind that C, whether it's 0 or not, has to be a constant, and 0 is a constant. Sorry, an integer. C has to be an integer, and 0 is an integer. So this tells me that this number is congruent to that number mod A. A is congruent to A mod n. Why? Because the difference, maybe I should have said it this way. If their difference is a multiple of n, that means that those two values are congruent mod n. But that's what I have above. I wrote that their difference is a multiple of n. That's all I had to do. The second one says that if A is congruent to B, then B is congruent to A. By definition, A congruent to B mod n, that implies that A minus B is a multiple of n. In fact, that's if and only if. And if I multiply both sides by the same number, whatever I write here will be if and only if this. I'm going to multiply both sides by -1. But that's the same as -kn. Sorry. I mean, it is true, but it's not the way I want it. I want it to be an integer times n. Oh, so B minus A is an integer times n. That means B is congruent to A mod n. You can interchange those two whenever you like. The third one is the transitive law. I need to show that if I'm given that A is congruent to B mod n, and B in turn is congruent to C mod n, I need to show that A is congruent to C mod n. That means that A minus C is some multiple of n. That's kind of on the side. Well, this here tells me that A minus B is Qn. This here tells me, I'm going to put it underneath, that B minus C is Rn. If I add them, -b plus B is 0. That's going to cancel out, and A plus -c, well, that's the same as A minus C. That's the left-hand side. The right-hand side, I'm adding a number of Q's. I have number of n's, excuse me. I have Qn's, and somebody gives me R more n's, I'll have Q plus Rn. Ooh, you mean A minus C is a multiple of n? That implies that A is congruent to C mod n. Exactly what I said we wanted. A minus C to be some number times n. That's the third one. The fourth one says you can add two of these congruences, like equations. If A is congruent to B mod n, and C is congruent to D mod n, I want to get that A plus C is congruent to B plus D mod n. Well, that means that A plus C, minus B plus D must be some multiple of n. Well, this tells me that A minus B is Qn, and this tells me that C minus D is Rn, and if I happen to add these, I'll get A minus B plus C minus D is going to be Qn plus Rn. But I can add the A and the C first, minus, and then I can add the minus D the minus b and the minus d. Well, I factored out the minus, so it becomes plus b plus d. And this is equal to, I can factor out the n. I have q plus rn's. Ooh, you mean this minus this is a multiple of n. Yeah. That implies that this quantity and this quantity are congruent mod n. You may say, but wait a minute. This is the sum, that's the sum. When did we ever talk about sums? Well, we did, not to be nice, but we did talk about sums when we were in the 2nd grade. And when you add two numbers, you get one number. When you add two numbers, you get one number. So if you prefer, maybe in this case, you can think of a plus c as one number. You can think of this as one number. So we have one number is congruent to another number mod n. That's perfectly fine language. Okay, a plus c is definitely one number. Sometimes you want to think of it as two numbers. But right now, it's probably best to think of it as one number. Okay, so this problem had two parts. We wanted to show that if you add the a and the c, and you add the b and the d, everything works out nicely. Now we want to multiply them. We want to show that a times c is congruent to b times d mod n. That's what we want to show. Okay. That is, I want to show that AC minus BD is some multiple of n. Okay. It's good to know what you want to show. That way you stay somewhat focused. Well, let's see. I'm going to leave AC as AC. But this here tells me that B is A minus QN. And this here tells me that D is C minus RN. So, BD. B is A minus QN times D, which is C minus RN. Well, this is AC minus AC minus ARN minus CQN plus QN times RN. Well, I hope it's clear that AC minus AC is gone. We need to take this away, so it becomes plus. We need to take that away, so it becomes plus. And we need to take away that last one, QNRN. And I do want to write one thing. I want to write that this top line, that this line is equal to AC minus BD. I mean, I have the AC, I have the minus, and I just wrote B and D differently. That's all I did. And what happened is some very nice things. From each of these terms, I have an N. I don't care that the last one has two N's. It has an N. I'm going to pull it out. Minus QNR. That is, here it is. AC minus BD is a multiple of n. That implies that AC and BD are congruent mod n. That's number 4. Number 5 talks about just adding C or multiplying by C. So, you're given that A is congruent to B mod n. And you want to show that A plus C is congruent to B plus C mod n, and that A times C is congruent to B times C mod n. This is what we want to show. Well, this here tells me that A minus B is a multiple of n. Right? This one, okay, so I like this. I can add C. As long as I take it away. Oops. I can add C as long as I take it away. Forget the C for a moment. This is still A minus B. And the C's cancel out. So it's still A minus B. And this is Kn. Ah, you mean this minus that is a multiple of n? That means this is congruent to that mod n. If this minus this is a multiple of n, and 2 things, this isn't 3 things. This is an integer, this is an integer, and k is an integer. Then this follows. Okay. Now, let's do it for multiplication. We're given that's true. Well, that means that A minus B is a multiple of n. Let's multiply both sides by C. So this says CA minus CB. Rearranging a little bit is, well, okay. Using associative law, actually, this is CK times n. You mean this minus that, those are integers, is an integer multiple of n? Yeah. That means CA is congruent to CB mod n. That is, remember, this came from this. It's just saying that you can multiply both numbers by C. Can you multiply by 0? Well, let's see. 0 times A. So, it's not going to matter that A is congruent to B mod n, but if I multiply the left side by A by 0, and I multiply the right side by 0, are they really congruent? That is 0 congruent to 0 mod n? And you better believe it. When I subtract those numbers, I do get a multiple of n. I get 0 times n. So, yep, that's valid. So you can even multiply by 0. It's not going to be helpful, trust me on that, but you can do it. And okay, so the proof ended right here. And I did it for sum, adding C to both sides, and then multiplying C on both sides. Number 6 states that if A is congruent to B mod n, that implies that A to the k is congruent to B to the k mod n, and this is for any k that's positive and lives in the integers. Now, we're going to do this by induction, but we're going to have to use the rule that we just proved, rule number 4. It says that if A is congruent to B and C mod n, actually this is probably just 4B. There were 2 parts of 4. A is congruent to B mod n, and C is congruent to D mod n. Then you can multiply the A's and the C's, and it'll be congruent to when you multiply the right side, B times D mod n. Okay, we're definitely going to use that. Now, we're going to prove this by induction on k. So, if k is equal to 1, we know that A is congruent to B mod n, but that surely means that A to the 1 is congruent to B to the 1 mod n. Main reason is A to the 1 is A and B to the 1 is B. So it's true for k equal 1. Now, for k is equal to R, assume that A congruent to B mod n implies that A to the R is congruent to B to the R mod n. And we also know, let me say it the long way, A congruent to B mod n implies that A is congruent to B mod n. Nothing magical there. A is congruent to B mod n. But now we're going to invoke rule number 4. It says that you can multiply those two and it'll be congruent to the product of those two mod n. The thing is, those are real numbers. That's A to the R plus 1, and it's congruent to, let me do it the same order. The top, B to the R, times the 1 below. That's B to the R plus 1 mod n. And somewhere I had to say, when k is equal to R plus 1, show that A congruent to B mod n implies that A to the R plus 1 is congruent to B to the R plus 1 mod n. Well, I did show that. I did show that. And I got it from showing or assuming that A is congruent to B mod n. I even carefully wrote it. So we nailed this one. That completes this proof. Actually, this set of proofs. If you love seeing math like this, subscribe to my channel. Click the like button. Tell your friends about my channel. Leave a comment. Most of all, see you guys in the next video. And don't forget, watch and learn.